Okay, let's look at some review of nozzle or momentum equations, and we're just going to see some examples here. So first of all, we're just going to review what is the nozzles. In nozzles, we have a clear example of a momentum equation. You can see the nozzle. There's a lot of liquids try to just force the nozzle off the end of the pipe. So we have like a velocity at the beginning, pressure, and the cross-section area at the beginning of the before contraction. After contraction of this nozzle, like the device, we have the outlets, and we have like a pressure and at the outlets, and with the cross section of the area of the A2, and velocity output is like of the jet is V2. So once we're just going to write the equation of control volume, we can just algebraic force. We can just write like a P1 A1 minus P2 A2, which is like in the reverse direction, minus FR, which is in the reverse direction. Can you see like a negative direction? In the positive direction is like a P1 A1. So this is algebraic forces. And on the right hand side, rho Q V2. V2 is like the positive direction minus V1. V1 is like a positive direction. So because the P2 is subject to the atmospheric pressure, so because of the atmospheric pressure is 0, we can just remove this term P2A2, and if we're just gonna solve this equation for PFFR, the external force, FR is calculated as a P1A1 minus rho Q. So if you just can rearrange this one to the right hand side or to the left hand side and multiply by minus, so and take other terms to the right hand side, we can just write this equation to calculate the FR. So let's look at one example, clear example here. So we have, for a situation in this diagram, we just are supposed to calculate the force exerted to the water nozzle. So this is like the things that we have for this kind of like the assumptions. Discharge the 0.65 cubic meters per second. Diameter 1 at D1 at the beginning of the nozzle is 0.3 meters. And D2 is like a 0.2 meters. Okay, so the diameter changes or reduces from 30 to 20 centimeters. And the pressure at the beginning is 171.76 thousand newtons per square meter, and the density of the water is 1,000. So we have like equations like this one, as you know. We're just going to look at this equation. So we're just going to need to just write these calculations. So we have the momentum equations is this one. So before solving this one, we from the previous slide, remember we just have this general equation for the momentum. Then we simplify this equation to this one because the atmospheric pressure for P2 is 0, and FR can be calculated by using this formula. And the other formula is like a continuity equation. Continuity equation before for the entrance and for the exit point. We have the continuity equations of the Q. We can just write V1A1 is equal to V2A2. So if you're just going to write this one as well, and if you simplify A1 and A2 as like a pi d squared, so we're just going to have like a V1 P or pi D1 squared is equal to V2 pi D2 squared. So you're just going to simplify that one, and if you cancel out the pi from two sides, we're just going to write V1 D1 squared is equal to V2 D2 squared. So first of all, you're just going to use the continuity equation because we have like a D1 D2, and we have the velocity. We don't have the velocity here, so we need to just look at this like a Q. We have the Q already here, but we can just easily use the Q with the D1. We can easily calculate the V2 as well. Let's see how we're just going to go ahead. So first of all, we just calculate the V1. V1 is like a Q, okay, divided by area, like the pi 0.3 squared, okay, and 4 is just comes next to the like the Q, okay, and the V1 is calculated now 9.196 meters per second. You can calculate the V2 the same as the V1, okay, Q divided by the A2. Or you can just use this formula. V2 is equal to the V1, okay? If V2 is equal to the V1 times D1 minus D2. D1 is like a 0.3 divided by 0.2. All of them, the ratio is to the power 2. Okay, so the V2 is like a 20.691. So as you can see here, this velocity is really high, but so it's not like a normal application of the water transportation. Normally just used for, for example, firefighting, they're just going to use this amount of the velocity, 9 or even 20. Can you see the velocity change twice, more than twice actually, from 9.196 to 20 point something. So with this kind of like V1 and V2, we're just going to go ahead and calculate the FR. We need to substitute everything in this, the top formula on the right-hand side. So the P1, A1, A1 is like a pi, D 0.3 squared over 4, minus, and rho Q, rho is like 1,000 times Q is like a 0.65, times V2 minus V1. V2 is like a 20.691, minus V1 is like a 9.196. So if you're just going to solve this equation, so you're just going to calculate the FR, all of them, you can just factor like a thousands from, you don't need to just apply to the equations. And finally, we have like a 4.67 thousand newtons. So that is the FR. Okay, so we said that 4.67 or 4,670 newtons applies, the force applies to this nozzle from left to right. That's the equation, and that's like example for nozzle.